Hello and welcome to Mind the Stats. My name is Mohammed Radisi and I'm here to talk about binomial distribution applications. My mission is simple: to take a difficult subject and break it into small sections to make it less of a challenge. I'll walk you through one or more examples to reinforce what you've learned. I welcome your feedback, questions, and suggestions. Please subscribe to my channel for future sessions or improvements, and thank you in advance. You may be familiar with process capability for continuous data and how to calculate capability indicators such as PP, PPK, and process sigma, for example. In this session, we'll explore how to determine these indicators for attribute data. We'll be dealing with binary data that takes one of two values, either true or false, on or off, etc. We've learned from other sessions that categorical or binary data can be counted and proportioned. When dealing with binomial data, an inspected unit either has or has not a predetermined quality. If we're checking for dents on a part, the part is either clear of dents or has one or multiple dents. A unit with zero defects is called non-defective. In the binomial world, a part with one or more defects is called defective. When sampling for defective units, we're only getting a defective rate for that specific sample. So to predict the failure rate for the entire population, we're going to do some estimation. Binomial distribution allows us to calculate an upper bound with some degree of uncertainty. Next, we're going to see how we can go from DPMO to process capability. In the binomial distribution world, each part or sample is considered one opportunity. DPMO stands for defect per million opportunity. And it's computed by dividing the number of defective units by the number of units inspected. If no defective units are found, then we can still estimate the worst case probability of defects using one sample proportion. So the question is, knowing what the DPMO is for a certain process, how can we translate it to process capability? And the answer is, we'll explore it in the next few slides, how to go from DPMO to z-score, from the z-score to PPK to process k-sigma. I mentioned earlier that even if we take a sample and find zero defects, we can still estimate the upper bound reject portion. And I'm going to show you how you would do that. Say we sampled 30 units from our production process and found zero defective units. We go to Minitab and we use one sample proportion. The command is, as shown here, stat basic statistics 1 proportion. As shown here on the right, we select summarize data, where we enter the number of events, which is 0, and number of trials is 30. That's a sample size of 30 and reject rate of 0. And then we click on option, which allows us to pick the confidence level. And in here I'll pick 50 for now and click OK. And this is the output we'll get. The result is 0.0228, which is, if you multiply it by a million, you get 22,840 defect per million opportunity. That is the upper bound. So your reject rate is between 0 and 22,840. So next I'm going to show you how you can go from DPMO to z-score. But first we need to understand what DPMO is and what z-score is. DPMO represents the portion of defects or defective units, and the histogram to the right here. The shaded area, that's the defective portion. If you take DPMO value, like an earlier slides, 22,000 something, and you divide it by a million, you'll find the non-conforming portion. The universal measure of capability is called z-score or sigma score, or simply z or z value. So in this example that we have here on the right, z, first of all, is the number of standard deviations between the mean and a point of interest. Usually the point of interest is either the upper limit or low limit of the specifications. In this histogram, the point of interest is exactly at 5 sigma, so which means that z is equal to 5. So because there are 5 sigmas from the mean to that point of interest. And the area under the curve is equal to 1. So if you subtract the portion of non-conforming portion, or DPMO divided by 1 million, from 1, then you can use a software package like Excel or Minitab to calculate the inverse of cumulative distribution. And I'll show you how you can do that in Minitab next. Before I show you how you can calculate the z-score using Minitab, I'd like to show you the relationship between z-score and PPK. The capability index, whether we're talking short-term CPK or long-term PPK, short-term is usually a sample that you take either during a day or a couple of days. Long-term is when you're dealing with months of production or a year worth of production. But essentially the formula for calculating both of them is the same. Point of interest, like the spec limit, minus the mean divided by 3 times the standard deviation. Or in a formula form, CPK or PPK, it's the closest spec limit minus mean divided by 3 sigma. In prior slide we talked about Z, and Z is equal to the difference between a point of interest and the mean divided by the standard deviation. So if you compare the two equations, 1 and 2, the difference really is 3. So essentially PPK is equal to Z divided by 3. We're not going to dwell too much on the K sigma or process sigma, but it's take it for now as 3 times PPK plus 1.5. And in future sessions I will discuss this in more details. Now that we know how DPMO, Z, and PPK are related, we can take an example. We go from DPMO to the proportion of defects by dividing that DPMO value by 1 million, which represents the proportion of defective units. The area under the curve, as we said, is equal to 1, so if you subtract this proportion here, or this portion here, you end up with 0.97716. Now using Minitab, if you issue this command, calc probability distribution in normal, we use a normal distribution, and standard normal has a mean of 0 and standard deviation of 1, and in here we selected the inverse cumulative probability, so entering what the area under the curve for the accepted units of 0.97716, and you click OK, this is the result you get. So essentially this number here represents the Z value, 1.998. Dividing it by 3 gives you PPK, and that's all you needed to do. In the previous slide, it was for one-tailed SPAC. This slide here is similar to the previous slide. The only difference is that we're dealing with two-tailed specifications. So we have a min and a max. So essentially, we do the same thing. You take DPMO value divided by a million. That gives you the proportion of failures. But you divide that by 2 before you subtract it from 1. That gives you this area here under the curve. And from that, we do the same thing. We issue the calc command in Minitab, where we enter the new value in the constant here, and nothing else had changed. We click OK, and you get the new value of Z. So Z value here is 2.276. You divide it by 3, and you end up with a new PPK. As I mentioned earlier, we're not going to spend too much time talking about process sigma or K sigma. I will have a special session where we talk about Six Sigma methodology, and that's where I get into some more details. But for here, we looked at the data two ways. One, I'm looking at it as one spec, a one-tail spec versus two-tail spec. And essentially that gives you a range of 2 PPKs, 0.66 to 0.76. If you apply the formula that's on this slide here, K for K sigma is equal to 3 times PPK plus 1.5. We'll revisit this when I talk about Six Sigma methodology in a future session. But essentially, if you apply this formula here, 3 PPK plus 1.5, you end up with a K sigma that ranges between 3.4 and 3.8. This concludes this session, but if you happen to learn a thing or two from this, then please like this video, and better yet, subscribe to my channel for future releases. Please let your classmates or colleagues know about this, and thank you very, very much.